fact live. All right. So for our linear regression, entering in the data, pulling up the stat calc, doing all that fun stuff. What is the R value that we got? Technically, I'm going out of order here, but this is the wrong. What is the value of R? What's the correlation coefficient that we found?
0.991.
Very good. So for A, got that R was equal to 0.991. And what did we find for our equation here? Y equals AX plus B. What is A? What is B? 897X. And then you do plus negative. That's fine. Plus negative 588. That looks good. You can also do minus instead of plus negative. Either way is fine. I do not care. Technically, the order is reversed here. The R that we have is the correlation coefficient. This equation is the linear regression. Now, a couple of people did the LN regression instead of the linear regression, which also got an interesting result. What was the R value that we found for the LN regression? Yeah, this is an R equal to 0.909. So you'll notice when you are in StatCalc that there are a whole bunch of different regressions that we can run. There's like a linear, there's a quadratic, there's a cubic, all that stuff. You could run any of those, and those are going to give you different R values. And what we can notice is actually this R value is pretty strong, right? 0.9 is actually pretty decent as far as like our R value goes. And again, today we're going to talk about what it actually means to be strong, what is strong enough in this case. But it turns out that this other regression does a pretty good job of fitting the data. But which one does a better job of fitting the data? And why? Linear does better, and why is that? R value is closer to 1, exactly. So what we would do, in theory, is we would run all of these. We would compare each of the R values to one another, and then we would pick the regression that gives us the strongest correlation and be happy. So just a quick thing to note, there are two LIN regressions. Both of those are interchangeable. The LN regression is a completely different function. That is a logarithmic function, and it can still give you an R value, and that's cool. And in this case, it's a slightly worse fit than our line, which is interesting to know. Very good. Okay, for part B, we're trying to figure out the number of bacteria. We're trying to predict, using this equation that we just got, the number of bacteria that we will have after a certain amount of time. Now, for this, it's really, really important that we understand what our X is and what our Y is. We totally could have swapped these two. You would get a different value for A, a different value for B. Importantly, you would get the same value for R, which is interesting. And you would just have a different equation, and that's totally, totally fine. You would just use that equation instead. But what's important here is that we identify, are we being given an X or are we being given a Y? In the case of B, what information are we being given that we're being told to look at what's going on after 23 hours? Is that X information or Y information? That's X information. With how we put in this data, this is the equation that you would get if you used hours as X and bacteria as Y, which is certainly what I would default to. Again, you don't have to do it this way, but if you did it the other way, then you'd be looking at a Y information instead of an X information. That's fine as well. Okay, very cool. So we're given an X value. Looking for a Y value, what do I do with that particular X value in order to figure out what the Y value is? Plug it in for Yeah, plug it in for x. So y in this case is going to equal our 43.897 times 23 minus 37.588. What did we get when we simplified all this down? 907. Depending on where the rounding was, I've heard 971, I've heard 972. I think the first time I ran this, I got 972.014 or something. But does it make sense to talk about having like 0.01 of a bacterium? Not really. And so we'll just say that we would expect to have about 972 bacteria. And then finally for C, what are we being given here for C? Well, so in this case, we're looking for number of hours, and we are given a number of bacteria, which is our Y value. Very good. And so this is going to be that 300 is equal to 43.897 times the missing value of X that we need, minus 37.588. Quick review. What's the order in which I need to do this? First, we add the 37 point blah, 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 and then we are going to divide the 43 point blah, 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 blah. And what do we get for our X value? What's our guess? 7.69. If you wanted to be extra precise, just to show that we are in fact looking at 3 digits and rounding those 3 digits, you could have a 0 here. I do not need you to. That's totally fine. This many hours. Very good. Questions with our bell work here? This is like as comprehensive a question as I could possibly give you over 1.2. So if this felt really, really comfortable, then I would expect you're in a pretty good position for the quiz tomorrow. No questions, feeling okay? Not too horrible. All right, very good. What we are going to be doing today is we are going to take a look at some of our first like truly statistics exclusive content. What we were talking about yesterday, and kind of something that we gloss over, I asked you to find the R value. I didn't really ask you to interpret it. Certainly that is something that I would expect you to be able to do. For instance, what could we say about our correlation given this particular value of R? Positive correlation because it's a positive value of R. And is this one strong or weak relatively? It's pretty strong. It's actually very strong with that 0.99. Is about as close to 1 as we're realistically going to. Actually, that's not quite true, but it's very close to 1. Right? So we're pretty happy with that. What we're going to be looking at today is taking that idea of being pretty happy with this R value and giving that some rigor. In particular, we are trying to figure out, is this R value actually good enough for us to even justify running this linear regression? Would we even be happy with the guess that we generate? And what are kind of the factors that that's going to depend on? What are we going to be looking at for that? With my algebra class, when I have kind of taught linear regression and scatter plots in the past, the rule of thumb that I gave them was that if the R value is like 0.8 or more, then it's pretty strong. If it's like 0.3 or less, then it's pretty weak. And if it's in between those two, then we might describe it as moderate. That is all garbage. We are throwing that out. We are going to do a lot better than that. Okay, so this is our goal, is to actually try and put something to the, is this R value good enough? Can we actually claim that we see a correlation here? I want you guys to take a moment, go ahead and enter in this data while we set up. Since I've done this a couple of times, mine is already entered. My other classes, this is just like 2 minutes of me standing there silently, pressing in buttons. Maybe not 2 minutes, like 30 seconds of me doing that. But I'm going to have you guys do that. We are going to be introducing a few new ideas that are going to be very, very, very universal with a lot of the statistical methodologies that we are going to be using throughout this class. The first thing that I want to draw attention to is what is highlighted here in the kind of salmon-y color here, an alpha value. So in particular, we are being asked with an alpha value of 0.05 to determine whether what we see is what is called statistically significant. Okay, so let's unpackage this alpha value. 0.05, which I'm going to kind of refer to as like 5%, is not the only alpha value that we are going to see. It is, by and large, though, the most pervasive alpha value that there is going to be. There are certainly going to be use cases where there are others. This is, generally speaking, the one that we default to, though, is this 5%. We're going to look at a table here in a second. You'll notice that there's also an alpha value of 0.01 or 1%. Similar interpretation, which we'll talk about here, but 5% is kind of the industry default, I would describe it as. And we'll talk much, much later about like what advantages of different alpha values would be. But it's just a value that's given to us. In particular, this alpha value is telling us something about how okay we are going to be with a random result. For instance, let's imagine we are flipping a coin over and over and over again. And we want to know if the coin is weighted or not. Is it a cheat coin? Are we being scammed? Or are we scamming someone else, I guess? Right? And so we take that coin and we flip heads or tails, and we do that 4 times. And every single time we do that flip, it lands heads. It's a crazy, crazy, crazy coincidence that that happens 4 times. We'll talk about probability a little bit later, but it's a pretty unlikely event for that to happen 4 times just randomly. Now, what we would expect is that the more times we flip coins, the less those kind of outlier values occur. For instance, if we flip a coin 4 times and get 4 heads, that's not necessarily all that suspicious. But if we flip a coin 10 times and get 10 heads, that's a lot more suspicious. If we flip a coin 1,000 times and get 1,000 heads, then we should be very, very, very skeptical about the nature of this coin. Which would be to say that random chance is okay. We're kind of okay with random chance influencing it when we don't have all that much data. But the more we flip the coin, the more skeptical we become as these less and less and less likely events tend to occur. This alpha value is taking into account how okay we are with random chance being possible to generate our result. For instance, you can confirm this if you like, there's about a 6.25% chance of flipping a coin 4 times in a row and getting heads all 4 of those times. If our alpha value was set to 5%, that is not crazy enough. That is not random enough. That is not unlikely enough for us to say this coin is probably a cheat. By the 5th time we flip the coin, all of a sudden the chance of that happening is down to 3%. If our alpha value is again set at this 5%, that is too random. That is too crazy of a thing for us to happen. We are not okay with seeing that 3% in comparison to the 5%. There's probably something else that's going on that's been set aside. If we wanted to be even stricter, if we wanted to really, really know if this coin was in fact a cheat, we might set that alpha value to be stricter. Maybe rather than getting suspicious when our likelihood of occurrence dips below 5%, maybe we set it to 1%. Now all of a sudden we're not suspicious when 5 heads come up. Or we're not suspicious when that 6th head comes up. But by the time that 7th head has come up, again, it's so unlikely. It's a less than 1% chance that that would happen randomly. We're very, very suspicious. Something else is probably going on here. This probably isn't just random chance. All right, so the alpha value, how much random chance is there that we could get this result? In this case, we're going to be looking at values of R just randomly, just sporadically. And the idea is that it's harder to get really, really strong values of R by just random chance. We saw yesterday, we were looking at a correlation that looks like the X and Y values were just like completely random, completely scattered. That's pretty easy to generate by just randomly picking and assigning X values and Y values. But as that R value gets stronger and stronger and stronger, we would expect that to be harder and harder to produce by just luck, by just flipping coins and being unlucky or lucky. Okay. In other words, if it's 5% randomness, then we are looking at a 95% chance that what has shown up is showing up because of a correlation. And this is kind of just the metric that we set. Okay, we're okay with 5% randomness. We'd like to be 95% sure that what is there is a result of the correlation, not just a result of random chance. And an R value that is particularly strong is going to be one that is kind of harder to disprove. So that's what the alpha value is attempting to communicate here. Now, alongside that alpha value, we are going to need an R value of comparison. This is going to be that R value that represents that 5% chance of random just luck. It's an R value that's going to be pretty strong. We have to beat this R value in order to show that what's happening isn't just random chance. And it's going to be set for us. We don't need to find this. This is going to be given to us. In particular, if we look here at this table that we have, what we have is a list of R values that are going to be basically determining what's going on with just 5% luck, 5% random chance. Okay, couple of things to observe about this table. First thing that I would like to note, we have this DF thing going on there. That means degrees of freedom. What this is basically saying is that as we flip more coins, as we collect more data, we should be more confident in our conclusion. For instance, if we were to flip 10 coins and 7 of them were to come up as heads, that is not as strong a result as flipping 100 coins and having 70 of them come up heads. So degrees of freedom is basically our way to incorporate the fact that as we collect more data, we would expect that randomness to kind of fade into the background. Notice that that R value that we have to hit gets smaller and smaller and smaller the more data that we collect. Outliers start to pop up less and less, or start to influence what we have less and less. And so if we are collecting a lot of data, we don't really have to worry nearly as much about just random chance swinging us one way or the other. Like one unlucky coin flip is not going to influence something very much if what we have collected are 50 coin flips. Now you'll notice that the degrees of freedom is not actually the sample size. So we defined yesterday n as being our sample size, which is just like, again, the number of points that are in our data. The degrees of freedom are, for whatever reason, n minus 2. There is actually a reason to this. It's not just completely random and arbitrary. It's also not always n minus 2. Different tests will have different degrees of freedom. The reason this is set at n minus 2 is because it doesn't make sense to run this test if you have 2 or fewer points of data. If you have 2 points of data, your R value is just going to equal 1 or negative 1. It's only once you add that third point of data that we can actually start saying something interesting about whether or not it's statistically significant. And so to avoid having too little data, we set the degrees of freedom. We start at n minus 2. We start at an n value of 3. So a little bit arbitrary, but like you don't have to worry about it. For our purposes, for this test, it's always n minus 2. Looking at our sample here, looking at our at what we've got, what's our sample size, and then what's the degrees of freedom that would go with this sample size? How many data points do we have, and then how many degrees of freedom does that correspond to? 8 data points, which means we have, what do we have to do to the n? Minus 2, and so we have 6 degrees of freedom, which just comes from the 8 data points, number of data points, number data of points, gives us a degree of freedom of 6, which just tells us that we are looking at this row on our table. Okay. The other thing that we have to worry about is the alpha. If we're okay with 5% randomness of a result that could show up randomly about 5% of the time, then we'll have our alpha value be at 5%. If we want the randomness to be less likely, then we would set our alpha value lower. That's the alpha value of 0.01. Notice that for pretty much every single row here, the alpha value of 0.01, that 1% chance, is a stronger correlation. It's harder to hit that 1% than it is for that 5%, which is like what we should expect, right? If it's harder to hit stronger correlations, then being more picky about our data should mean that we are looking at stronger correlations. So what is the actual value on our table that corresponds to 6 degrees of freedom with the alpha that we set at 0.05 or at 5%? 0.707. This is what we are going to describe as the critical value. It is this R is equal to 0.707. In terms of our interpretation, we would expect this R value to show up about 5% of the time just randomly. Specifically with 8 data points. All right, so this is like the lowest possible value of R that we could be looking at in terms of the strength, such that we would be happy with saying that there's something fishy going on. Okay, questions with kind of what we're looking at. This is a lot of this is just kind of set up that I am kind of gearing towards this problem. We're going to actually talk about what the problem is asking us to do and how we're going to do it here in a second. But any questions with like what this table is, what our alpha is trying to communicate, how I found that what we're supposed to be using for this data set is this 0.707, anything about like the general setup structure, what we're looking at here. That's counting the number of XY pairs that we have for our data set. Yeah, so it's the number of data points that we have. Good question. Other questions here? Okay, so what is it that we are even trying to do with this? Well, our blanket assumption, what we are going to describe as the null hypothesis, is that the correlation coefficient that we see is just a result of luck, that there isn't actually a correlation between these variables, that instead this pattern appeared because we got lucky or unlucky. And if that is the case, then there's no significance to even talking about this data, really. It doesn't make sense to run a linear regression because our idea is that it's probably just luck. Again, that is referred to as the null hypothesis. Generally speaking, the way we communicate the null hypothesis is we are going to use H sub 0. And that is that there is no correlation between our variables. Now, to be precise and persnickety, rather than saying that there's no correlation between X and Y, you should probably actually tell me what X and Y are. You could define off to the side. I think someone in here may have done that yesterday or the day before, where you defined off to the side, like this is what X represents, this is what Y represents. That's great. That's totally fine. If you want to make a little key for me and then say we're saying that there's no correlation here, perfect. Beautiful. You're done. But if we wanted to be very, very precise here, we might say something like our null hypothesis, well, the null hypothesis, H sub 0 colon, there is no correlation between the number of attendees from year X and the number of attendees from year Y. Something like that. This is what we assume to be true. Our goal, kind of, if we have a goal, this is what it is to prove this wrong. We're not ever going to really be able to prove this right. That's not what we're trying to do. We're trying to prove this wrong. We are trying to instead state that the opposite is what is happening. What's the opposite of there being no correlation between my two variables? There is a correlation between my two variables. Very good. This is referred to as the alternative hypothesis. Because it's alternative, you'll see this denoted as H sub A. And this just says that there is a correlation between X and Y. I guess to be consistent with my abbreviation, we'll say that there is a correlation between X and Y. So the null is that this is just random, this is just lucky or unlucky, depending on your perspective. The alternative is actually, no, it's not luck. It's because these variables are connected in some way. There is a correlation that is going on here. We assume the null, we're trying to prove the alternative. And the way that we prove the alternative is by showing that the R value that we get for the data is in fact more unlikely than our benchmark critical value. More unlikely in the context of R values corresponds to what? Stronger or weaker? Stronger. It's harder to have a strong R value. It's more unlikely that a really strong R value is just going to pop up by accident. It's easier for us to get just a weak R value randomly. And so in order for us to definitively say that there must be a correlation by this whole like 5% randomness, we're okay with that, is to say that in fact the R value that we are looking at is stronger than this critical value. Can someone run the linear regression on this data and tell me what they find for our R value? $791. Is this a stronger R value or a weaker R value than our critical value that we defined up here? This is stronger. So notably, this is stronger than 0.707. So we were saying that if there's like a 5% chance that this is just random, but 95% certain that it's not, then we're okay with that. This is even more unlikely to get by random chance. It's harder to get this than that benchmark that we were saying that we were okay with. And so we're pretty confident in our conclusion because we have an even harder to get, an even more unlikely event. We are going to go ahead and say that or the way we describe it is we would say that we reject the null hypothesis. It's too unlikely for this data to group this way by just random chance. It's a less than 5% likelihood that this would even show up at all with an R value this strong with just a 5% chance. Since that's so unlikely, we're pretty confident, we'd say 95% confident, that in fact what we are looking at is because there is a correlation. And so for our summary, we might say something along the lines of because our test statistic of R is equal to 0.791 is stronger than the critical value R is equal to 0.707, then we reject the null hypothesis, which is the same thing as saying that there is a correlation between X and Y, between our two variables. Yes. So. Is it every time that the correlation coefficient is larger that we reject the hypothesis? Pretty much. So every time our R value is stronger. So for instance, a good example that I would use, if the R value that we had found was negative 0.791, is that R value strong enough for us to reject the null? If it was the only thing we're changing is the R value that we got was negative 0.791 instead of 0.791. Is that stronger than this test value that we see, or not this test value, but this critical value that we see of 0.707? Yeah, because the negative doesn't do anything to the strength of our correlation, right? The negative just tells us, is it a positive correlation or a negative correlation? This is actually a really important point. So technically what we're comparing is like the absolute value. And whenever the absolute value is larger, then yeah, we just reject and we're done. But this is actually a really, really good point. You'll notice here on this table, PPMC, which is like the method that we're doing, it's called like Pearson something or other. I don't know, it doesn't matter. For this particular test, you'll notice that it is called a two-tailed test. The only thing that we are trying to prove with this test is whether or not there is a correlation. We're not trying to say that it's positive. We're not trying to say that it's negative. And in fact, you'll notice in my conclusion, I don't say that we are confident that there is a strong positive correlation here. I'm not saying anything like that. I just say that there is a correlation, right? Two-tailed is the whole, it could be rejected by a negative number or it could be rejected by a positive number. An example of a one-tailed test would maybe be to asking us to prove if there was a positive correlation between these two. Now, all of a sudden, an R value of negative 0.93333 isn't actually good enough to prove a positive correlation. In fact, it probably proves the opposite. It probably is proving a negative correlation. And so it would fail, say, like a one-tailed test. You don't really need to know the difference between the two for now. It's two different tests. It's two different tables. If you need to use a two-tailed table, then I'll give you the two-tailed table. And the hypothesis for the two-tailed is it can be confirmed by either rejecting because it's too big negative or too big positive. The only value that I'm not like 100% certain of and should probably look up, but also I'm kind of lazy, and it's also like never going to show up, so I'm not particularly worried about it, would be whether or not you reject. Like, let's say we ran our linear regression and the R value that we got because the world hates us was exactly 0.707. What on earth would we do then? It should never happen. I would assume that you would fail to reject. I would assume that you wouldn't have enough evidence to be able to say that's rejected. 0.708 would be sufficient. 0.7071 would be sufficient. But I think if we matched the critical value, that we would probably not be able to reject. But I could be wrong on that. That's just my intuition. But it will never happen. So it's not really something that we need to worry about. Generally, it'll be pretty clear, like, do we reject or do we unsuccessfully reject? Other questions here? Okay, so we found our R value. Our R value was really, really strong. So strong that it's very, very unlikely to happen by chance. There's probably about a 2% chance that that would happen by chance. And I say that because notice if our alpha value had been 1%, that this R value wouldn't have been good enough. So it's good enough if we're okay with 5% error. But if we shrink that down to 1%, then all of a sudden it's not good enough. And there are plenty of situations in which you would want to set your alpha value even lower than 5%, where maybe rejecting when you're not supposed to reject, when it is in fact just random, like kills somebody. That would be a really good situation to set your alpha value really, really, really low. Or that might be that it's not that important to incorrectly reject, but that failing to reject when that happens, for instance, if you were getting a flu test and the flu came back and it said, no, you don't have the flu. We have successfully confirmed that you do not have the flu, when in fact you do have the flu. That's more problematic than telling you that you have the flu when you don't. And so that kind of comes into like, where do we set this alpha value or anything? We don't need to find it. I'm always going to tell you. We'll talk about more about why that would be important, maybe towards the end of this course. Has to do with what's called type 1, type 2 error. And it's all very, very complicated. It's not that complicated, but it's all part of this process. And it's why we have these various different alpha values. The default is the 5%, though. Okay. So if the R value that we find is strong enough, if the event, the statistical event, is unlikely enough to happen, then we say that we reject the null hypothesis, that the alternative hypothesis is true. If it is not strong enough, then we have not done anything to prove that the null hypothesis is true. So this is a really, really kind of annoying, verbal, obnoxious, this is very common in statistics, element that is actually very important to get right. Failing to reject is not the same thing as proving the affirmative that the null is in fact true. For instance, let's say that we had gotten an R value of just 0.7 or 0.6, something like that. It doesn't mean that there is no correlation. It means that we don't have strong enough evidence to say that there is correlation. There might be, there might not be, we can't really say for certain, and so we would then move on with our lives. We wouldn't assume that there's correlation, but we certainly would not rule out the possibility. We do not reject, or I will often say we fail to reject, if the R, and technically it's like the absolute value of the R, right? If the R value, test statistic, which is the one that we get from our data, if it is too weak. Too weak just being weaker than the critical value that we are comparing it to. And we successfully reject the null hypothesis. We confirm the alternative if what we found, if the R value here, test statistic, is what I would describe as strong enough, where again, strong enough just means bigger than, more powerful than, stronger than the value that we are comparing it to. So we fail to reject if it's not strong enough, not saying that that makes the null hypothesis wrong, or that makes the null hypothesis true. We just can't say that it's wrong. And we successfully reject, we successfully show that the null is wrong if, in fact, the R value is unlikely enough, if it is strong enough. All right, so let's take a moment. We're trying to figure out from this data set if there is a correlation between the number of students in a particular class and the grade that that class receives. Is there a significant, statistically significant correlation here? So we're going to run our hypothesis test, trying to figure out, do we have enough data in order to say one way or another whether class size and the final grade on average are related? Take a moment. And if they are related, if we do in fact reject, then this wants you to also run a linear regression to make predictions. If we fail to reject, it doesn't make sense for us to run a linear regression, because why are we trying to make predictions based on a correlation that we're saying we don't even know is there? You'll use the same table that we used prior for this one as well. It's the same. Although not necessarily the same degrees of freedom. So this is your data. And then we'll use this table to figure out what we're comparing that R value to, but that'll be like the that looks like the right R value. And then what is the critical value? What is the value of yeah.
Where is that? There's 1, 2, 3, 4.
Yes.
No, not right here. My bad. All right.
That looks like the right R value. And then it's just a matter of figuring out what are we going to compare that R value. What is the benchmark for anything stronger than this tells us that something's going on, but anything weaker isn't enough. We're going to use the table to figure out that. Okay, that R value looks good, and then it's just a matter of what is the critical value that we're going to be comparing to. What's that like minimum R value that tells us something is 5% is the alpha, and that alpha will correspond to an R. It's the table that we used as a prior. We'll use that one. It tells you that you're doing it at
Critical value.
yeah, in the not on the so you're using that table for the 5% in the problem. You'll notice that it says that we're
The test value. I don't know how to figure out that.
I didn't really
The test value is the real one. I like this.
Sure. Nice. Yes. Yeah, so you're gonna run the linear regression.
Yes. It's just like the.
Yeah, I was wondering, I was like that. It's really low, okay.
I've never seen those. I saw bars.
Red. And then it's just a matter of figuring out no correlation or that goes along with it. And we need to figure out from what we're gonna compare this to. So we don't even necessarily need an equation yet. We might not even want to create the equation. If that R value isn't good enough, we don't want an equation. We want to say if this R value isn't good enough, there isn't enough here to say that there's a correlation. So by figuring out where on the table that
Yeah.
Object, very good, comparison. Again, it's very since we're not trying to prove causation, we might say something along the lines like they're just not. Because proving that something isn't caused, we would have to run through the whole thing. This is just saying like there isn't even any connection. Like and since you've defined your null like that, your conclusion would just be something along the lines like because the strength of the R value is weaker than the critical value, we fail to reject the null. What'd you find for the? That's okay. Negative number would just mean negative correlation.
Oh, but the absolute is the absolute.
And we check the absolute value to actually look at the strength. We're going to talk about that tomorrow. All of what we're looking at is correlation, or at least possibly correlate. Oh, you mean for like the conclusion?
Yeah.
Okay, so if our R value is really strong, then there is correlation. What really strong means is if it's better than this. So this is like the benchmark of it has to be at least this strong for us to be able to say that there's correlation. Because this is weaker, we can't say that there's correlation. Now, we don't know that there's no correlation. So we want to be very, very precise. But we can't say that there is. So the way that you might phrase it is the null hypothesis is that there is no correlation. And we have failed to reject that null hypothesis. We have been unsuccessful in our attempts to prove that. Yep, this looks good. And so what would we say about, can we claim that we have
It's a whole set, so it's kind of just
I agree.
Reject the null.
Yeah, because this test, the test value that we got from data is weaker than that bench. So in terms of like the summary here, we would say something along the lines of like the null hypothesis is that there is no correlation. And because the test value that we found is weaker than the critical value, we have failed to reject that. And then because we failed to reject it, it doesn't make sense to make the equation, because the equation is basically saying like these are correlated and this is the function that connects. And we're saying like we don't even know that they're
It's kind of with the average
okay.
MP.
This looks really good. This is the correct conclusion.
Imperfection to it.
In terms of like on like a you might say something like the null hypothesis, and you can even
Oh yeah, that would be helpful.
There's no correlation between the two. And then in our conclusion, we can say something along the lines of like, because this R that we found for our data is bigger than the critical value. We failed to reject the null, and then you can even. But you just want to make sure that you define what that null hypothesis actually is.
Yeah, I want my major. Major.
This is like the comparison value that we're comparing to. Absolutely correct, but this is the test value. And so what can we say about the strength of this compared to this? It's going to be weaker. And so do we have enough evidence to say that there's a correlation here? Do we have evidence to say that there's no correlation there for sure?
Hard at press.
We just don't know.
They're fairly easy. Kind of staff we do.
Okay, so this is the comparison point. That looks good. Yeah, so the hypothesis that we write here is basically always going to be that there's no correlation. So the conclusions are going to be like what we write. But the hypothesis itself, particularly the null hypothesis itself, is that there is no correlation. And what we're trying to do is either reject or fail to reject. We're pretty much done for the day, but I'll play it.
Yes. I think it's cool. Exact practice.
Okay, so the null that we have here, H, is that there is no correlation. And the conclusion is because this is bigger than yes, looking at that one.
We would do it for
The thing that I hate is.
So we're going to look at which is just, it's in yeah, so we need to figure out the number of the way we figure out the way.
No, it's only he.
No, it says all. It says I'm a new one.
What?
And then that's what we're going to figure this R. So you just look into is this going to be smaller or easier?
Yeah, we'll have a square. We'll have a triangle. Basically, you just throw that.
Yes. That's so funny.
You're into this is wrong because 28 is more complex. Now the negative. Yeah, you can round it up, but it still does.
It doesn't have to teach all. I think he said he was gonna have it.
Is equal to that. Okay, do you want to should we take a look here? We're going to run through this. Sure. Okay, let's take a look. Let's take a look here at what we found for this example. Let's start with our hypotheses. What is the null hypothesis? What is like the blanket assumption that we go into this problem thinking? No correlation between, no correlation. And here again, if we can be specific, it's best to be specific. What are the two variables that we are comparing? Students, which represents the class size? Yeah, so like students is like number of students in a class. And what is the other variable? The grade that they get. So class size and maybe like final grade. Okay. So that's the blanket assumption that we make. If that is false, what is the alternative option? Just very simply. Yeah, that there is a correlation. Between class size and grade. There is a correlation between those. Okay. So that's what it's asking us for in this like correlation piece. Right? So the null is that there's no correlation between the variables. If that is false, then there must be a correlation between those variables. Fairly simple. What is our sample size? Yep. Charlie? Yeah, 6, which means how many degrees of freedom do we have? This is 6 minus 2, which is 4 degrees of freedom. Okay. So let's take a look at our table here. What is the what's our alpha value for this problem, and also for pretty much every problem we're going to work? 0.05 at 5%. What is the value on our table that represents that kind of baseline at 5% with 4 degrees of freedom? That's going to be that 0.811 that we see here. So this is going to be that comparison value of R that we are going to use. That is our critical value. This is R should be equal to 0.811. That's the like minimum strength to reject. We got to be at least that strong, otherwise no dice. All right. What is the value of R that we found for our data? 0.686. Very good. Pretty strong. Is that strong enough to, how does this compare to our critical value? It is weaker than 0.811. Not strong enough. Is it because of the negative? No, it's just because 0.6 is less than 0.8. Right? One of them is closer to 0 than the other, or one of them is closer to the bound than the other. The absolute values of them when we're compared, one is weaker than the other. And so if our test statistic, if the data is not strong enough, do we have enough evidence to reject our null? No, and so we fail to reject the null hypothesis. Okay. As far as the summary goes, if we want to be very, very precise, we might say something along the lines of, because the test statistic of R is equal to negative 0.686 is weaker than the critical value of R is equal to 0.811. We fail to reject the null. If we wanted to interpret this as far as what that means about correlation, there is no strong evidence that there is correlation between these variables. Certainly not strong enough for us to accept. No strong evidence that X and Y are correlated. Doesn't mean they're not. It just means that the data that we have found doesn't let us say that there is. Is that a question, Valencia? Are you just judging, or do you have a question? Sure. Yeah. All right. Questions here with our hypothesis testing. 1.3. Which will not be on the quiz. Right, 1.1, 1.2 tomorrow. I'm not going to ever give you a quiz over something that you haven't had like sufficient time to incorporate or ask questions about. Is that a question?
For this, the values.
Yeah.
Whatever.
Yeah.
If we do have that on the quiz or test, are you just gonna provide one of those?
Yeah.
Okay.
Yeah, whatever tables, stuff like that that you need are always just going to be provided. Yeah. Yeah. Any other questions with our process here? Okay, so tomorrow we have a quiz over the linear regression, scatter plot, correlation stuff. 1.1, 1.2, so not this, but just 1.1, 1.2. If you have completed the 1.1, 1.2 online Pearson assignments, then you can get up to 2 bonus points on the quiz tomorrow. So if you've already done those, or if you have those finished by the time we have the quiz tomorrow, you'll get up to +2 on the quiz. So that's my incentive to do that. Those and the packet, the homework packet that has the crossword on front, are not due until the test. So if you have not finished the classwork by tomorrow or the homework by tomorrow, you're not getting late grades or anything like that. That won't happen until the test. But my advice going into the quiz, which would be the same as a sports coach going into game day, is you should probably practice before you have to prove that you can do it. That would certainly be my advice. To that end, I want to give you guys the rest of this class to work on the classwork, ask any questions that you have. I will be roaming around